Hello everyone, today let's solve the problem number 104, maximum depth of a binary tree set. So what the question states here, we have to find the maximum depth of the binary tree, right? So they have clearly mentioned here, we have to find the maximum depth of a binary tree, which is defined as the longest path from root to leaf node. Means maximum depth is nothing but it is defined as longest path from root to the leaf node. This is maximum depth, right? So that's what we need to find, the maximum depth of the binary tree that is defined as the longest path from the root to leaf node, right? So let's come to the first example here. You can clearly see here in this case we have here, this is we will be considering from 0. Binary tree indexing starts from 0, basically 0 1 here, 0 1 2, right? So this is the maximum depth we have, basically either we can consider this one or 0 1 to this one. This is the maximum depth we have, right? So when giving this one, we can just give +1. We have to just add +1 here, because indexing, this is 0 based indexing, and the output they are expecting in 1 based, right? So just add +1 to it. In this case it is 3, so we need to return output as 3 here on this case. This is fine. So let's come to the second example here. Same thing, 1 null 2 we have, right? So here in this case 0 1, so 0 1 we have. So I can draw in this way, just give me a second here. This one will be 1, this is null, left we don't have anything, 2 we have this one. So this one, just ignore this one, don't have anything here. So this will be 0 1, right? Basically indexing starts from 0, they are expecting 1 based here, so +1 here in this case, this will be 2, so we have to return 2 in this case, right? So this is fine. So I hope the question is completely clear. What we need to do is completely clear as well, easy to understand, right? So let me clean up this one, just give me a second here. First let's discuss the approach, followed by the edge cases one by one, and then finally write the code and discuss the complexities for the code that we have written. Initially let's discuss the approach first. So here the first thing that we need to note down here is we will be going with the recursive DFS. So we'll be making use of the recursive DFS approach, right? So I have considered the same example, the first example that they have given in the question. So we have already discussed this one, basically 3 9 20 null null 15 7 we have here. If I come here, right? So this one 0 1 2 here. So this is 0 based indexing, so +1 we will be adding. In this case the maximum depth will be 3, right? So we have already discussed this one. So output that we need to return here is 1. So let's quickly discuss the step by step execution here, right, or the explanation. So first we will start from the root node 3. So this is the root node, right? So this is the root node. We will start from the root node 3. So we will recursively find the depth of the left subtree, means here this one first. So this will be 0 1, right? So this is fine, nothing but the value 9 they have given of the left subtree, node 9 they are speaking of, or value 9, right? It has no children, so depth is quite obviously 1 here. So this is having, this doesn't have any children, right? The node 9 I am speaking of, this doesn't have any children, so this will be 0 1, so the value will be 1 in this case, right? So next let's move on to the next step here. We will recursively find the depth of the right subtree, node 20 means right one, this one we are speaking of, right? So this is fine, 20. So here in this case node 15 has node 15 has no children. Here node 15 has no children and node 7 has no children as well, right? Node 15 and node 7 has no children here in this case. So depth is 1, depth is 1 in this case. So minimum of 1 comma 1 plus 1 is 2 here in this case, right? So this one 2. So minimum of 1 comma 1, this is 2 in this case, right? So this will be 0 1 2. So we will be adding +1, right? So maximum of left 1 and right 2 and subtree +1 for root 3. For root 3 +1 we are adding, right? So because root we have to consider here in this case. So root we have to consider, this one we have to consider, and this one 20 we need to consider, and either 7 we can go with or we can go with 15, right? So this one we will start basically from 1 1 2 3, or indexing starts from 0, you can just add +1 in, we can go in this way, right? So just give me a second here. So the final depth will be 3 here in this case. The final depth will be 3. So the final output that we got here is 3, which is equivalent to the output, this one. Output they have given for the example 1 in the question, right? So the approach works absolutely correct in this case. So now we are completely familiar with the approach. As we are completely familiar with the approach, let's discuss the edge cases one by one quickly, right? So I'll just come here. So first one is for the empty tree here, right? So first edge case is for the empty tree here. Just give me a second here. First edge case is for the empty tree. Root is null. So we don't have anything. So output will be quite obviously 0, right? Root itself is null. In that case, output is 0. So this is the base case, right? Basically, this is base case. Just remember this one. If root is null, we have to return output 0. This is very important. This itself is the base case. Just remember this one. So let's move on with the second edge case, single node. We have only one node here. Then the depth will be, we have root, only root here in this case, root node. So here in this case, the output will be quite obviously 1. Let's move on with the third edge case here, left skewed tree or skewed left. In this case, we have 1, 2, 3, 4, null, null, null. Completely skewed towards the left skewed tree, right? So here in this case, output will be quite obviously 4. Depth we have to find out, right? In this case, 4. They have clearly mentioned it is a left skewed tree, right? So you can just draw that one for if you want to understand, right? So in this case, this is skewed right. We know the left and right skewed tree, right? I hope you guys know. We have previously discussed about the left and right skewed tree. So if you don't know, you can watch the previous videos as well, right? So in this case, this one 1 null, 2 null, 3 null, 4. This is completely skewed. Let me draw here 1. This one is null. So this one is 2, again null. This one is 3. This is completely skewed towards the this one. What do you say? What do you call for this one? Right skewed tree, right? 0, 1, 2, 3 plus 1. As we need the depth, it is plus 1 as it starts from the 0, right? So this will be 4 here in this case. Same goes with the left skewed tree as well, right? So you can just draw in the same way, but it will be skewed towards the left, right? So this is fine. So these are the 4 edge cases that we need to keep in mind. First one is for the empty tree, second is for the single node, third one is for the skewed left or the left skewed tree, fourth one is for right skewed tree, right? So these 4 edge cases we need to keep in mind. So now we are completely familiar with the edge cases as well as the approach. As we are familiar with the edge cases and approach, it will be easier to write the code. Let's start writing the code. So first, let's go with the base case. If node is null, then the depth is 0. We know this one. First edge case we discussed, right? So I can write in this way. If root equals null, means in that case we have to return 0. I'll just go with return 0. This is fine. So the next part is we are making use of the recursive DFS, right? Or we are recursively calculating the max depth from the left and right subtree, and we have to add 1 for the current node, right? So as again I'm telling, binary tree indexing starts from 0. That is the reason we are going with plus 1 here. Don't get confused. Return 1 plus, so I'll just give math.max of, here in this case, max depth. Let me copy this one. Max depth of root dot left. This is fine. And max depth of here root dot right. This is fine. So this is it for the code. So let me format the code once and let me hit the run button. Simple one, right? So let's see whether this works. We have error here. Max of max depth. This has to be small m. Did I type this one? I should have copied the function. This is fine. So let me hit the run button again. So now we can clearly see the sample test cases are getting passed. Means the code works absolutely correct in this case. Let's see whether this works for all the test cases or not. So let me hit the submit button. So here you can clearly see all the test cases are getting passed. Means the code works absolutely correct in this case, right? So let's quickly discuss the complexities for the code that we have written. So the approach that we went with here is recursive DFS or recursive depth first search. We know this one, right? So what would be the overall time complexity here? The overall time complexity would be big of n. And why it is big of n here? Because we are visiting each node exactly once. We know this one, right? It will lead to the big of n complexity. So overall time complexity would be quite obviously big of n here in this case. So what would be the space complexity here? The space complexity would be big of h. Why it is big of h here? In the worst case, because it is big of n for the skewed tree, right? So we can just write big of h because for a balanced tree, recursion depth is logarithmic n or big of logarithmic n. For the skewed tree, the recursion depth can go up to big of n. So overall space complexity, we can just write it as big of h in this case, nothing but height, right? So here in this case, the time complexity is big of n and the space complexity is big of h for the code that we have written, right? I hope the complexities are clear and I hope the code, whatever that we have written, is completely clear as well. For now, this is it. Thanks for watching, guys.